Assalamu alaikum students, welcome to lecture 10 of this Fluid Mechanics 2 course, and in this lecture we are going to start a new chapter, that is chapter number 11 from your Munson book, and that chapter is related to compressible flows. And this is very interesting because so far we were dealing with incompressible flows, and the way we differentiated these two flows was that in incompressible flows the density was not changing, and now in compressible flow we are going to account for that change in density. So for incompressible flow we saw that density was constant, and now for compressible flow we are going to take that density as changing. This is the main difference that we defined, and now we will have to define some other state properties for these compressible flows, because by changing the density of the fluid, of any fluid, that can be liquid or gas, there will also be a change in the pressure, temperature, etc., the internal energies, the enthalpies, the entropies. So these are the state functions, the state functions of any fluid that we are going to study, that how will they change when we are talking about compressible flow, and how are we going to account for the change of the state properties when we are talking about compressible flow. So let's move forward and see that how the compressible flows are important, because the measurement of high flow velocities requires theory for compressible flow. So the high flow velocities, the fluid flowing at high speed, they generally require to be treated as compressible flows. So that's why we study the compressible flow theory. And then the gases that are being used in the turbine engines are generally compressible. So that's why the study of compressible flow is also important in that regard. And also many aircraft fly fast enough to involve compressible flow. We know that aircraft use turbojet engines to actually compress the air-fuel mixture at a very high compression rates, and use that compression ratios to propel the aircraft forward and generate fast speeds. So that's why the compressible flows are important in the fluid mechanics course. And now we are going to talk about some basic of thermodynamics that we saw in the thermodynamics course, but we are going to revise them to actually give you a fresh idea based on the perspective of the fluid mechanics. So the first equation that we are going to talk about, the equation of state for an ideal gas. You are familiar with this equation, that is P is equal to rho RT, and here the P is the pressure, rho is the density, R is the universal gas constant, and T is the temperature of the gas. So now that we are accounting for the change in density for a particular gas, then the pressure, temperature will also change, and then we are going to put specific value of R that is constant for each and every gas. So R represents a constant for each distinct ideal gas or a mixture of ideal gases, and that R is again a ratio of two things. This is the universal gas constant. This is the universal gas constant whose values are given at the end of this book for different gases, and this one is the molecular weight of a ideal gas that we are taking into consideration. So this is the universal gas constant, and this is the molecular weight of a specific gas that we are going to take in our analysis. Then again we will calculate R as such. So this is again the part of the ideal gas equation that we are going to use, because now the density is changing, and with that the pressure and temperature also are going to change. The next property, here we have covered the pressure and temperature. The next property, the important one, is the internal energy, and internal energy is defined with the help of specific heat capacity at constant volume, and that specific heat capacity at constant volume actually accounts for the change in the internal energy with the change in temperature. So how does this equation comes out to be like this? For that we will have to see the equation that we got from our first law of thermodynamics, that any change in internal energy will be equal to the change in the heat content of the system plus the work that is done by the system or on the system. So this is the equation that we get from the first law of thermodynamics, and when we are talking about this equation, we will actually also talk about the heat capacities. Heat capacities are of two types. One is at constant volume that you see, and the other is a constant pressure. So why we use constant volume with internal energy, and in this slide also we will also use the constant pressure. So how does this equation comes out to be like this? Let's see that this is the equation that we get from the first law of thermodynamics, and the equation for heat capacity. For heat capacity is basically the capacity of any material to absorb a certain amount of heat and how much heat it can absorb. So that is represented by C, and that C is equal to Q over delta T. That the heat absorption is dependent upon the change in temperature. So the higher this value, the lower will be the heat capacity, and the lower this delta T, the higher will be the value of this heat capacity. So the heat capacity formula is C is equal to Q over delta T. That means that the heat capacity is dependent upon the change in temperature, that the change in heat capacity of any system will be due to the change in the temperature. So if we arrange this equation for Q, then it comes out to Q is equal to U minus W. So let's put that here. C is equal to U minus W over delta T. Now we can have two scenarios. Let's take a piston and cylinder arrangement. This is a cylinder, and inside there is a piston. And also let's try another diagram. So now let's take two scenarios, and let's say that here is a certain amount of gas inside this cylinder and also inside this cylinder. And let's change the internal energy of this gas inside this cylinder, and there are two ways. One is to supply any amount of heat. Let's say there is fire burning here, and that fire will result in the change in temperature of this gas inside. And what we do for our initial case, for this case one, what we do, we see that the piston is not moving. The piston is closed shut, it is welded shut, and the cylinder is not moving. So what will happen? Only the heat content of this gas inside this cylinder will change. So only this variable in this equation will change, and due to this assumption that we have taken that the piston is closed shut, it is welded shut, it is not moving, so no work is done, no work will be done in this scenario, and this term in this equation will be 0. And also if we take this apply this scenario on this equation, so here the work will be 0 because the piston is not moving. Only the temperature of this gas is increased by burning certain amount of any liquid or fire below this cylinder, and that will result in the change in internal energy only. So this scenario accounts for the specific heat at constant volume, because the piston is not moving, so the volume is constant, and the only change in the internal energy is due to the change in temperature of the gas, that is due to the fire burning under this cylinder. So that's why we take CV is equal to U delta T, and that's why you are seeing this equation right here, that CV accounts for the change in internal energy due to change in temperature of the gas. So that's why we take the specific heat at constant volume with a change in internal energy with respect to change in temperature. So hopefully that was clear. I will again come back to this diagram when we talk about enthalpy, and again we will write these equations, but let's now write some equations or see some equations for the change in internal energy, that how we will account for the change in internal energy for a specific system. We can rearrange this equation like this, and then we can integrate that for two extremes, and that will give us the change in internal energy for this temperature, for this change in temperature at constant specific heat at constant volume. And it can be simplified and written like this, that this equation gives us the change in internal energy at constant volume. So now another important fluid property is enthalpy, and enthalpy, again we will use these equations, but let's clear out the area. We have talked about pressure, temperature. We are already familiar with that how they will change with density. Now we talked about the internal energy and how that is related to the specific heat capacity at constant volume. But now let's talk about the enthalpy. And enthalpy, as you know, is equal to the internal energy plus work done. It is also U plus PV. This equation you have seen is U, that is internal energy, plus PV, that is the work done, and V can also be written as 1 over density. So that's why you are seeing this equation like this. And again, now let's take another scenario where there is a piston and a cylinder and a piston, and now the piston will move when we supply heat from under the cylinder. When we supply certain amount of heat, then now the piston will move. So that equation that we wrote, that U is equal to change in the heat content plus the work done on the system, that the internal energy will change when we supply heat to a system or do a work on the system. So again, using that equation for specific heat capacity, that is specific heat capacity was equal to Q over delta T, and now again rearranging that U for U minus W over delta T. So now if we are saying that the piston is also moving and the heat content is also added to this gas inside this cylinder, so what happens, that the internal energy is also changing and the work is also being done, because now the piston is moving. The piston is moving, and as you know that work is equal to F into D. So if it moves about here, so a certain amount of distance will also be covered and a certain amount of pressure force will also be applied on this piston. So the piston will move and work will be done. So now we can see that this change in volume, the volume is now not constant, but this change in volume will be compensated for the change in pressure. So we can write this as Cp, that this is the specific heat capacity at constant pressure. The pressure is now constant, the volume is not, and the internal energy will change along with the work will also be done on the system due to the change in temperature that is occurring by adding heat to the system. So now we can write the equations like this, that Cp is equal to change in the enthalpy due to change in temperature. So you can see that the subscript P, that is a constant pressure, and here we saw the subscript V at constant volume, but at constant pressure work is also done. So here we can write this equation like this. Instead of enthalpy, that is the internal energy plus work done, it is also internal energy plus work done. So now we can see that Cp is equal to change in enthalpy over change in temperature due to the change in temperature. So now we can write this equation like this and simplify it a bit more to find the change in enthalpy for our gas. That can be any gas at any 2 points. These are the state functions. That's why we are talking about 2 points at point change in enthalpy at point 1 and point 2, and that is delta H, and that delta H will be equal to this function. And now again we discussed two state functions. One was the internal energy and the other was enthalpy, and we saw that enthalpy is equal to change internal energy plus the work done. Now let's combine these equations with the our equation of state for ideal gas. And now we saw that the internal energy is also a function of temperature. This is our equation of state for ideal gas, and the enthalpy is also as a function of temperature here defined. So now let's combine these equations and derive some other equations. We can actually write the this equation, that H is equal to this change in enthalpy will result in the change in internal energy plus R dt. We can substitute this for this right here and actually write it like such. Then by dividing dt on both sides, we can actually get dH by dt, du by dt plus R, and we know that dH by dt equals to specific heat capacity at constant pressure. This will account for specific heat capacity at constant volume plus the universal gas constant. So we can write our equations like this. These are our equations for the heat capacities at constant pressure, constant volume, that is equal to the universal gas constant. Then if we talk about the specific heat ratio of these two specific heats, then Cp can be arranged over Cv, and please remember that Cp is always greater than Cv, because in Cv we are only adding heat, but in Cp we are also doing work on the system. So Cp will always be greater than Cv, and we can write this ratio like this. Then by combining these two equations, we can write further two equations, and that will be for Cp and Cv as such. Cp will be equal to universal gas constant multiplied by the specific heat ratio divided by this denominator, and Cv will be equal to the universal gas constant divided by the specific heat ratio minus 1. So these are the other terms for Cp and Cv. These are our constant specific heat capacity at constant pressure and specific heat capacity at constant volume. So these are some of our important equations. And in the next slide we are going to also talk about another state function, that is the entropy, that how will we going to account for the entropy of a certain gas. Now, so far we talked about pressure, temperature, that how they are related to the density by using the ideal state equation for the ideal gas, and the entropy and the internal energy, that how we are going to calculate when we are talking about the change in density. So how we are going to calculate the change in internal energy and change in enthalpy. But let's now talk about entropy, that how are we going to write equations for the change in entropy whenever we are talking about the compressible flow. That also means that the density is changing. So this is the very famous TdS equation that is written in a form of the same equation that we used for our from our first law of thermodynamics, and here it is the temperature, the change in entropy, the change in the internal energy, pressure, and the change in volume, or volume as we said it can also be represented as 1 over density. So this equation will be used, and we will use this equation that was written for the enthalpy, that is internal energy plus the work done. So we will totally differentiate this equation with respect to the pressure and density, and we will write it like this, that is the change in enthalpy is equal to a change in internal energy plus the pressure, and the change in 1 over density plus 1 over density into the change in pressure. We know that this term right here, that du plus p d in bracket 1 over rho, this is equal to TdS. So we will put this function right here and arrange this equation in this form. So now we have another TdS equation. So using this ideal state equation, the equation for the specific heat at constant volume, and again this equation right here, we will derive an equation for our change in entropy, and after integrating this equation we can actually write it in as a state function in the form of S2 minus S1, that will be a change in entropy at constant volume. We can also write this equation for the change in entropy at constant pressure by using these three equations. Again, this equation, the Cp equation that we derived in the previous slide, and this equation right here, we can use this equation to derive this term, and then we can use these two equations to see the change in entropy at constant specific volume and constant specific pressure. So these are the two equations. This is the change in entropy at constant specific volume. This is how it is, and the change in entropy at constant specific pressure. So these are the two equations that are going to be used whenever we are going to talk about entropy and the change in either constant volume or at constant pressure. So why is entropy important? Because changes in entropy are important because they are related to loss of available energy. Whenever we are talking about energy, we are also interested about the loss of available energy, because this is the major factor in every problem, that how much energy we are getting or how much energy is being lost from the available energy. Then changes in entropy are related to the changes in temperature, pressure, and density, as we can see from here that the changes in entropy at constant specific volume will be equal to the change in temperatures and the change in densities, and at constant pressures it will be equal to a change in temperature and change in pressure. So these are the terms that are interrelated. These are state functions, and by state functions we mean that if we have 2 point 1 and point 2, and if the system moves from point 1, changes from point 1 to from point 2, so it is independent of the direction, that if it takes this direction or if it takes this direction, we will be interested in the change that is from 2 minus 1. It can be enthalpy, it can be entropy, it can be temperature, and it can be pressure. So it can be any state function that we will be interested in. And now we are talking about the changes in the state function because our density is changing, because now we are talking about compressible flows. So that's why we are talking about these changes in the state functions. So the second law of thermodynamics requires that the adiabatic and frictionless flow of any fluid results in a zero change in entropy. That means that S2 minus S1 will be zero. That is according to the adiabatic and frictionless flow of any fluid in the second law of thermodynamics. And constant entropy flow is called isentropic flow. We are already familiar with that term. And for isentropic flow of an ideal gas with constant Cp, Cv, we get equations 11.21 and 11.22 that we derived for the change in entropy S2 minus S1 at constant specific pressure and constant specific volume. So what we will do, we will neglect this term S2 minus S1 is equal to 0, and then we will write those equations as such. So that this is how we can combine these two equations equal to 0 by making this equal to 0, because the flow is adiabatic and it is frictionless. So basically there is no loss that is occurring due to entropy. So this is how we can write this equation, and further we can simplify them by using these two equations. We can, and this equation we can actually write it as such. We can write it as such, and this equation again can be derived if we combine these three equations. If we combine these three equations, we can actually get in this equation where the temperature T2 minus T1, density P2 rho 2 minus rho divided by rho 1, and P2 over P1 are given, and we can again rearrange this equation in this form, that P over rho to the power k is a constant. So these are the equations that are basis of your thermodynamics, and we revise them because these equations are going to be used whenever we are going to talk about the compressible flows. So these were the state functions, and these were some important equations that we are going to use in our coming topics related to the compressible flows. Okay, so now let's look at this example in which we are required to calculate the change in entropy. And this is example 11.2, and in this example we are going to use the data from example 11.1, and this was the data that was given in example 11.1, in which we had a section of pipe of diameter 4 inches, and that pipe had two sections, section 1, section 2, and these were the values of temperature T1, pressure P1, T2, and P2. So this was the given data that air flows steadily between two sections in a long straight portion of 4-inch diameter pipe as indicated in this figure. The uniformly distributed values of pressure and temperature as we indicated are this such. So what we are going to do, we are going to find the change in entropy for this scenario, and now let's move on and solve this. So by assuming the flowing air in example 11.1 behave as an ideal gas, so we will assume that it will behave as an ideal gas because the equations that we derived previously, we saw the thermodynamic equations for different state functions like pressure, temperature, enthalpy, entropy. They were all for the ideal gas, that those equations were all considered for the ideal gas with changing density because they are compressible. We can then, what we are going to do, we are going to calculate the change in entropy between sections by using equation 11.21, that was the change in entropy at specific volume, and 11.22, that was the change in entropy at specific constant pressure. So we can use this equation, that is 11.21, and in this equation what we are going to do, we are going to replace this term with the ideal gas equation, that is in this form. We will apply the ideal gas equation and derive rho 1 and rho 2 and then write it as such. So what we are going to do, we are going to now put the values of pressure and temperature that we had in example 11.1 and calculate this value right here. So by doing so, what we can do, we can actually replace this rho 1 over rho 2 right here and write it like this in the equation 1. So by doing so, by substituting values already identified in example 11.1, problem statement and solutions in equation 3 with by solving this with the given values of pressure and temperature, what we get this value 4.56. So now what we are going to do, we are going to write the other values of Cv or the gas constant and calculate the change in entropy at constant specific volume. So let's do that. This is the value, this is the value of Cv that is converted into appropriate units, and this is the natural log of T2 over T1 plus the universal gas constant for air and the natural log of this value right here. So what we get the natural change in entropy at constant specific volume, that is for Cv. Now let's use equation 11.2 and see if this value changes or not. We will get write this equation as such, and then we will have to just input the values because we know all the values P2, P1, T1, T2, and we will input the values in this equation, and what we get the same change in entropy that we had from this equation right here. So what does this tell us? As anticipated, both equation 11.21 and 11.22 yield the same result for entropy change S2 minus S1. And here we will have to note one situation or one criteria that we are going to apply when we study the compressibility of different fluids in this chapter, that since the ideal gas equation of the state was used in the derivation of entropy differences equation, both the pressures and temperatures used must be absolute. It is saying that we derived these two equations previously, S2 minus S1, and we derived them with the help of our ideal gas equation, that is P is equal to rho RT, that is the pressure is equal to density, universal gas constant, and temperature. So we use this equation, and in this ideal gas equation we use the absolute values of pressure and temperature. So we use this equation in the derivation of these two equations, S2 minus S1 at constant volume and constant pressure. So what we are going to do, whenever we are going to put the values of temperature and pressure in these two equations, we will use the absolute values of temperature and pressure, and by absolute means that we will use absolute value of pressure, and by absolute pressure we means the pressure that is measured from perfect vacuum, that the reference point for that pressure is perfect vacuum, so that is the absolute pressure. And for temperature, that will be the absolute zero. We will take the minus 273 degrees C as the absolute reference point for measuring the temperature by taking the temperature as absolute. So whenever we are calculating the change in entropies, the value of pressure and temperature will be the absolute values of temperature and pressure.